So let me introduce today's speaker. So Dr. Bishal Deb. He's a postdoctoral researcher based at APSM in Sorbonne University, and he's employed by CNRS. He finished his PhD in 2023 at University College London under the supervision of Alan Sokal. His primary research interest is in enumerative combinatorics, in particular questions of total positivity in enumerative combinatorics. In his current position, he is learning about models in statistical physics and his interaction with combinatorics. Welcome, Bishal. Over to you.
Okay. So I hope I'm audible. I think I'm audible.
Yes, you are.
Okay. So let me first begin by thanking Monjilda for inviting me to give this talk. And when he asked me if I can give a talk, I decided rather than presenting any of my own results, it would be better if I introduce the subject, introduce this area of work. So I will be talking about coefficient-wise total positivity of Hankel matrices in counting problems. And so I have a weird affiliation. So I'm based at this LPSM lab, and the lab is split into between two different universities. But my office is in Sorbonne University, but then half of the lab is also in Université Paris-Cité. And there's also this other body, CNRS, and I'm officially employed by CNRS. So there's, because of bureaucratic reasons, I have to put my affiliation in this sequence. So in this talk, so as you can see, I have several slides. Feel free to interrupt me. I would prefer to be interrupted, and it's okay even if I do not finish all the slides that I have here, rather than just running through them very quickly. So this is the structure of the talk. I will first introduce the notion of, by the way, can you see my cursor?
Yes, yeah.
Okay. So I will first introduce the notion of total positivity. Then I will talk about total positivity of Hankel matrices. And we will see how that comes up in counting problems. And then I will introduce the notion of, add the first word to this entire thing, which is coefficient-wise total positivity of Hankel matrices. Then we will see some proof techniques, how one proves this property. And I'll end with some results and just brush over some results and some open problems. So let me begin. So a matrix of real numbers. So you have a matrix, its entries are real numbers. It is said to be totally positive if all its minors are non-negative. What I mean by this is you pick a finite number of rows, a finite number of columns. You take that square submatrix, the same number of columns, you take that square submatrix, and its determinant should be non-negative, and that should be true for all minors. That is, any finite square submatrix should have a non-negative determinant. So here I have said, so here we think of a matrix as an array of numbers and not as a linear operator. This is a highly basis dependent property. It's not basis independent, unlike something like positive semi-definiteness. If you change the basis and obtain a different matrix, it may no longer be totally positive. So you should really be thinking of this matrix as an array of numbers. Also, notice that in the definition, I have said nothing about the shape of the matrix. It need not be a square matrix. In fact, it need not even have finitely many rows and columns. This definition will still hold if you have a matrix with infinitely many rows and columns, as long as you ensure that all finite submatrices have non-negative determinants. And we will soon upgrade this property, and instead of considering real numbered entries, we will look at polynomial entries. So you might ask, like, why would somebody come up with this bizarre property? Well, it was independently discovered by two different groups in the 1930s who were not aware of each other's work at that time. So there was Krein and his school, and they were studying problems coming from mechanics and classical mechanics. And Schoenberg and his school, they were looking at distribution of zeros on polynomials, distribution of zeros of polynomials on the complex plane. So as you can see that right from its inception, this notion has had applications and motivation in different areas of mathematics, in applied and pure. So as I mentioned, Schoenberg's motivation was complex analysis and where zeros of polynomials lie, and Krein's motivation was applied maths. It was swinging of pendulums, some problems in oscillations, and some problems in classical mechanics. So I say that we use Schoenberg's terminology. By that, what I mean is, during this talk, whenever I use the word totally positive, I mean all minors are non-negative. Because if you are reading some paper, you need to be careful. Often writers use total positivity to mean strict positivity of the minors, not whereas in this talk, what I mean is minors are non-negative. So there's, depending on whether you're following Krein or whether you're following Schoenberg, there is a conflict in terminology. So let me now talk about Hankel matrices. So given a sequence A0, A1, etc., you have a sequence of real numbers, then you can construct this infinite matrix. So the rows and columns, the indexing starts at 0. The entry at row I and column j is A sub I plus j. For example, here the corner is A0, and then you have A1, A1, then you have A2, 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 you have A3, 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 and so on. So in this talk, we will mostly look at Hankel matrices. And so then we say that this sequence AN is Hankel totally positive if its Hankel matrix is totally positive. That is, this particular matrix, all its minors are non-negative. So one can ask, how do you prove such a thing? Okay, another thing that I should mention is it implies that the sequence is log convex, but much stronger. What I mean by log convexity is if you take any contiguous two minors, so for example, let's look at this minor A2, A3, A3, A4, then the non-negativity of the determinant, it means that A2 times A4 is bigger than A3 squared. And that is precisely what log convexity means. So if you have an minus 1, an plus 1, then log convexity says that an minus 1 times an plus 1 is bigger than or equal to an squared. But here it's much stronger. You have all minors are non-negative, not just the contiguous two minors. And okay, maybe I should also mention this. Of course, total positivity will imply that all the entries of the matrix are non-negative, simply because the entries themselves are the one minors. So A0, A1, A2, A3, they are all non-negative because they are just the 1 cross 1 submatrices. So they have to be non-negative. So now let me mention this fundamental fact which characterizes Hankel total positivity. So it's a theorem which is due to Stieltjes and combining a result of Stieltjes and Gantmacher and Krein. So of course the first statement is, so we have the following, so I'll give you some statements and all of them are equivalent. The first statement is the sequence is Hankel totally positive, by which I mean you take the Hankel matrix of this sequence and that is totally positive. This is equivalent to the following result. So there exists a measure mu on the positive real axis 0 infinity such that the sequence an is equal to can be obtained by integrating from 0 to infinity x power n d mu of x. And such sequences are called Stieltjes moment sequences. And such moment measures are called Stieltjes measures. So, and there is a big history of the Stieltjes moment problem, which I'm not going to get into. The third equivalent condition is there exists some other real numbers, alpha 0, alpha 1, alpha 2, and so on, which are all non-negative, such that if you take the power series, you sum over all a n t power n, then as an expression in formal power series, so you don't care about convergence when I write this identity, as a formal power series, this holds. So this is you obtain this continued fraction, alpha 0 divided by 1 minus alpha 1t divided by 1 minus alpha 2t, and so on. So this is a very fascinating statement. So the first is a statement about matrices and determinants. The second is a statement in analysis. And the third is a statement about formal power series. You have very different looking statements coming together, and this result says that all three of these are equivalent. And in fact, I'll tell you in a while why the third statement is in fact combinatorial. So any questions at this point? Okay, so let me continue. In fact, there is a fourth equivalent condition, which was only recently pointed out to me by L.V. Price. And it's much more recent than, so that's what, 50 years after, 43 years after Gantmacher and Krein. So it's a lot more recent. Well, this was, Flageolet's paper was still 44 years ago, but L.V. Price and Gutmann, this was only a few years ago. So you also have this fourth equivalent condition. And what this says is there exists a locally finite graph. So you have a graph. The graph could have infinitely many edges and vertices, but every vertex should have finitely many neighbors adjacent to it. So finitely many edges adjacent to it. And you designate a special vertex, O, you call it the origin vertex in this graph, and you put weights on all the edges. So you put a real number on all the edges of this graph. Then if it happens that this number an, so here an is a real number, if this number an is obtained by you start at the origin vertex, you go across the graph and you come back at the origin and you use 2n, and the length of your walk is 2n, you take all such walks and you add all the weights. So by the weight of a walk, what I mean is you take, so for each walk, you take product of all the edge weights that it traverses, and you add over all of these for all the weights. If this happens, then this is another equivalent condition. So Hankel total positivity is equivalent to the existence of such a graph with these edge weights. So, and this is like this was a minor result in a huge PhD thesis of Andrew L.V. Price, and he did many things in his PhD, but this is like one of the things, and his supervisor was Tony Gutmann. So let me mention that, yes.
So in this fourth equivalence, so this
Yes.
A could be an infinite sum also, right?
No. So there are only finitely many. If you have a locally finite graph, you'll have finitely many walks of a given length.
You are choosing all closed walks, so you are saying that it's the corollary.
No, all closed walks of length 2n.
There is a restriction on the length. Okay. Got it.
Yes. So you start from the origin and you come back to the origin, and you're only allowed 2n steps.
Okay.
And so in a locally finite graph, this will be finite. So it will be a finite sum. And so I was about to say that the equivalence between 2 and 3, this was already shown by Stieltjes. And in fact, Stieltjes also showed that 2 and 3 are also equivalent to not all minors of the Hankel matrix being totally positive, but certain minors of the Hankel matrix being totally positive. And then later, Gantmacher and Krein showed that if these minors of the Hankel matrix are totally positive, then all minors of the Hankel matrix are totally positive. And Flageolet proved this result in one direction, and L.V. Price and Gutmann proved it in the reverse direction. That is, if you start from the graph, you obtain. So what Flageolet showed was, if you have a continued fraction of this form, you can always construct a graph. And maybe sometime during this talk, I will show you how. So Okay, so let me proceed unless there are any further questions. So let's look at some examples of, I have given you some definitions, but I hope the definitions are not vacuous. Let's look at some examples of which satisfy these definitions. So many important combinatorial sequences are still just moment sequences. So I will use the word Hankel totally positive sequences and still just moment sequences interchangeably. They mean the same thing. So many important combinatorial sequences are still just moment sequences. So one example are the Catalan numbers. So this is the formula for Catalan numbers, and they count many things. In fact, there's a book by Richard Stanley with over 200 interpretations of objects counted by the Catalan numbers. And the Catalan numbers have this integral representation. So by the second condition in the previous theorem, it is a still just moment sequence. This is the measure, and you integrate this integral, you obtain Catalan numbers. And also, when I say have alpha n 1, 1, 1, 1, 1, 1, 1, what I mean is, in this continued fraction, if you plug everything to 1, what you get on the left-hand side are Catalan numbers. Okay. The second example is n factorial. They appear everywhere in mathematics. And here, the continued fraction coefficients are 1, 1, 2, 2, 3, 3, 4, 4, and so on. If you evaluate this integral, you're going to obtain n factorial. So all you need to do is you need to put in an x power n, you need to put in some stuff here, and you need to evaluate this integral from 0 to infinity. So here, I mean, there is no measure beyond 4. So, the entire measure is supported between 0 and 4, but you can go all the way up to infinity. If you can write an expression of this form, you're guaranteed that this is a still just moment sequence. Let's look at the next example. So these are the odd semifactorials. So you take products of odd numbers, 1 times 3 times 5, all the way up to 2n minus 1. And here the continued fraction coefficients are 1, 2, 3, 4, 5, 6, etc. And these numbers again have an integral representation. In fact, what I should mention is 2n minus 1 double factorial are the 2nth, the even moments of the standard normal distribution. So if you take the standard normal distribution and the odd moments are all 0, the even moments are 2n minus 1 double factorial. This is the exponential distribution. The moments are n factorial, and this measure for which gives you the Catalan numbers, this is Wigner's measure, which comes up in semicircle law of random matrix theory. So you see that there are fundamental sort of central limit theorems in probability theory, and their corresponding measures, moment sequences, are fundamental sequences which occur all around mathematics. So let me proceed. So how does one, okay, I have told you a theorem, and I have told you how, sort of you might be able to prove Hankel total positivity. But if I give you a sequence, how do you check? I mean, which of these three would you use to check if the sequence seems to be Hankel totally positive or not? And I mean, I don't give you the full infinite sequence. I want to do it on a computer. So I have, let's say, the first 10 terms. How do I do it? So there is an algorithm. And so again, so we have the sequence A0, A1, etc. And this is the continued fraction that we want. It's called the Stieltjes type continued fraction, or an S fraction in short. So now recall that the sequence is Hankel totally positive if all of these coefficients are, sorry, this is a mistake, are non-negative. So the inequality should be reversed. This is a typo. So this is what we want to do. We are given finitely many terms, A0, A1 up to AN, and we will compute alpha 0 up to alpha n. So, and if for the first n terms, these seem to be positive, then we say that we guess that this sequence is Hankel totally positive. This is what we mean by guessing Hankel total positivity. Now, let aj of t be the previous continued fraction, except you've done a shift. Instead of starting at alpha 0, alpha 1, alpha 2, you start at alpha j plus 1, alpha j plus 2, and so on. So thus alpha a0 of t is the original formal power, the generating function that we started with. And recursively, you can write aj of t is alpha j, but then what comes below is 1 minus alpha j plus 1 aj plus 1. I think there's an error here somewhere. The alpha j plus 1 should probably be inside the aj plus 1. Okay, but the point is you can use this recurrence and you can sort of extract the coefficients from this recurrence. You can teach this to a computer and ask it to compute more and more coefficients alpha j. So if you give a0, then you can ask the computer to solve for alpha j. This alpha j plus 1 should be inside and there should be a t outside. So if you give this recurrence to a computer, you can, so you give it aj, you can ask compute aj plus 1 for me and compute alpha j for me. However, this recurrence is very slow in practice because it involves divisions of power series. So if you're trying to do divisions of power series, it will be quite slow. Instead, what you do is, so here is an algorithm which was first, it is implicit in a paper of Euler in 1760. I think it was written by Euler in 1746, published in 1760. So those days it used to take 24 years before a paper would be published. And then somebody called Viskovatov in the early turn of the 19th century also rediscovered this. And my PhD supervisor, Alan Sokal, he was reading Euler's paper and he'd sort of worked out the algorithm by reading through Euler's paper. So, and he's written a nice expository article on this. So what you do is recursively define from the AJs, you define b minus 1 to be 1 and bj to be aj times bj minus 1. So you have bj minus 1, multiply it with aj and define that to be bj. Now if you do this, then you see that, so aj is in particular bj divided by bj minus 1, which is what you have here. And here aj plus 1 is bj plus 1 divided by bj. But then you can rewrite that and you can obtain something, the b's do not involve division. And this you can teach to a computer and you can do it very fast. And so this is the algorithm. Initialize b minus 1 to be 1. You are given the first n terms. Initialize b0 to be this power series and then put a big O after that. And then recursively compute from this formula, recursively compute alpha j and bj plus 1. So here you are only dividing the monomial t, but you are not dividing out a full power series. So that's still fine. And here the division is just division of numbers. It's not division of power series because it's just the zeroth, the constant term in the power series. If you do this, and so this runs very fast. And in fact, what Andrew L.V. Price did was he downloaded, there's this website called Online Encyclopedia of Integer Sequences. He downloaded the entire website. He ran this algorithm on all the sequences on the Online Encyclopedia of Integer Sequences. And he found 6,719 conjectures, minus epsilon, because some of them are solved. So, and yeah, so if you want to spend maybe a minute reading this slide, you can. So this is a slide which I've copied from Andrew's talk, which he gave at Permutation Patterns Conference. I can't see what's written on top. 2023. So that's last year. Okay, so any questions? So I want to show a demonstration now. Okay, so here I already have Euler's algorithm implemented in Mathematica. Let me just show you how fast it works. So, okay, so here is sequence to, yes.
Can you increase the font size?
Yes, I will. Thank you. Is this good now?
Yes.
Okay. So first let me just print out, okay, not the first 1000 terms, but the first 10 terms. So I will just print the sequence n factorial. And if I put this in here, compute it, it will give me the continued fraction coefficients, which I told you were 1, 1, 2, 2, 3, 3, 4, 4, and so on. And okay, you've seen I've already done it. But if I, for example, take the first 1000 terms in this, it can compute this in about 2 seconds. Well, right now my computer is running Zoom. When it was not running Zoom, it could do it in 1 second. And I'm guessing 1500 terms will take 8 seconds now. Let's see. So I'm not printing it out. I'm computing and I'm just printing out the time. So yeah, it took about a bit more than 6 seconds. Let's do Catalan numbers. So these are the Catalan numbers. So I have this code sequence to S-contract, which is Euler's algorithm, which Euler was doing by hand. And so as I said, Catalan numbers, it's 1, 1, 1, 1, 1, 1, 1. I mean, if you think I'm cheating, I can compute the first 20 and it's still 1, 1, 1, 1, 1, 1, 1. So of course, I mean, at this point, you stare at it and you guess a formula. And then you try and prove that formula from the first few terms. But let me also do something where you may not be able to guess a formula. So let me do the square of n factorial. So let me do n factorial squared. And you see, you have these horrible rational numbers appearing, and I cannot guess what they are. Alan Sokal cannot guess what they are. Maybe one of you could, but all we care is, okay, let me do min of this. So the minimum thing here is 1, so everything here is at least 1. All we want is everything to be at least 0. So far we guess that this sequence is coefficient is Hankel totally positive. Let me do 100. It's still 1. So there are instances where the continued fraction technique may not be able to give you a nice guess as to what the S fraction, the coefficients of the continued fraction are. But nevertheless, you guess that they are always non-negative real numbers, but you don't know, because the reason is because in this algorithm of Euler-Vyskov-Vatov, you're using division. So you'll have rational numbers appearing if you start with integers in general. You may not end up with integers always. Let's also do Fibonacci numbers. That's another. So let me first do the table. Fibonacci n. So let me print the, and going from 0 to 10. So here are the 10 Fibonacci numbers. However, this will not work. I need to start, because the first term here is 0. We want a non-zero start. Okay. Now let me plug this into my code and see if this is a Stieltjes moment sequence. It is not. You get -1 here in this computation. So the Euler-Vyskov-Vatov algorithm very quickly tells you that, in fact one can prove. So the Fibonacci numbers do not form, are not, their Hankel matrix is not totally positive. Okay, let me do, yes.
I have a question. So, suppose you have one Hankel sequence and you change the first number, you keep everything the same because there are
Yes.
a lot of conditionals involved, right? So what I'm saying is you perturb some of the numbers, a few of them, and then still they might be Hankel sequence. There is a possibility. But they might be that if you perturb them too much, they are not.
Yes.
So, or there are two sequences, Hankel sequences, which share some common terms. So,
yes.
are there results known in these actions? These are the questions that come to mind.
Yes, yes, certainly. I mean, the point is you have to check non-negativity of minors, and it's not strict. So it's I guess in a certain topological space. I mean, in the space of all sequences, I think this would be a closed condition, and so you are inside a closed set, and you can perturb, but you could easily go out of this closed set. So even a small change to one term in the sequence can perturb and take you somewhere else. Yes, that's correct.
Yeah, so because you have code making an experiment, right? Like just like that guy did on all the integer sequences, they could figure out. So if you take all the integer sequences, but now you perturb everything slightly and see, even after perturbation on let's say first 5 numbers or even one, because it appears in many minors, what happens? So that could be one
Yes.
experimental.
Yes, that is correct. And in fact, there are many interesting questions come up when you start thinking in that line of investigation. So this is part of an ongoing project on which I'm working with Andrew L.V. Price, and where we show that, let's say, that for the first finitely many, like first n terms, you guess that this is still valid. This is still, we guess that is Hankel totally positive. Then there is a minimum term, the n plus first thing, there's a minimum real number where it is Hankel totally positive. And if you take anything bigger than that, it is still Hankel totally positive. So if you have the first finite sequence, the next one, what do you put in? There is a minimum. So yeah, this is part of an ongoing work. But yeah, thanks for the question. So what I wanted to show you is
one thing, Bishal. I think that the Fibonacci number is not even log conflict, right? Or log conflict. This is just there is a negative, right? Negative fn times fn plus 2 minus fn minus 1 square is equal to minus 1 to the power.
So you can just take 3 times 1. It's less than 2 squared. Yes, that's correct. But let me do something else. So let me take these Fibonacci numbers. Okay. So these are the Fibonacci 2n. And now let's see what happens here. So this doesn't work as well. However, if you take the odd Fibonacci numbers, this is Hankel totally positive. The point is the continued fraction terminates at this point. So it's 2, half, half, and then it's all zeros. So the odd Fibonacci numbers, they form, their Hankel matrix is totally positive. All Fibonacci numbers are not, and even terms of Fibonacci are not. Well, so this is to show that sometimes you can also have continued fractions which can terminate. In particular, if you know what a rational sequence is, that is, if your generating function has a rational, if your sequence has a rational generating function, your continued fraction will have to terminate at some point. Okay, so let me go back to my slides. And yes.
So first question is that why you are focused on that totally positive? So why not any other thing like negative or something? If I take the negative, whether the equivalent condition.
So perhaps I'll. Is it okay if I come back to this question after the talk. I can say quite a bit on this, if that's all right.
Yeah.
Okay, so do remind me this question once I finish. So, okay, so let me now introduce this notion of coefficient-wise total positivity. So, the motivation behind this comes from refined counting and enumerative combinatorics. So, in enumerative combinatorics, we are not just counting by numbers, we are counting by polynomials. For example, we have Bell polynomials, so these count set partitions of the set 1 through n by keeping track of the number of blocks. Or you have Stirling cycle polynomials, so these count permutations with n letters having k cycles. Or you have the Eulerian polynomials, these count permutations on n letters with this statistic called descent. And so these polynomials can be and you can also have multivariate polynomials where you can count multiple statistics simultaneously. So this motivates, why not extend the notion of total positivity? Instead of having real numbers in the matrix, let's have polynomials. So we say that a matrix of polynomials with real coefficients is said to be coefficient-wise totally positive if all its minors, so minors are, you take square submatrices, compute the determinant. Since you have a matrix of polynomials, the determinants themselves are going to be polynomials, and we want that these minors should have non-negative coefficients. Again, in this definition, I have said nothing about the number of variables. You can have one variable, you can have multiple variables. And also, coefficient-wise total positivity implies point-wise total positivity. So what it means is, if you start with a matrix with matrix of polynomials and you substitute the variables to non-negative real numbers, then all such substitutions will give you a totally positive matrix in the sense which I introduced at the beginning of the talk. However, the coefficient-wise total positivity is much stronger. You do not have a both ways implication. That is, if you can do it for all real substitutions, then it implies coefficient-wise total positivity. That is not true. So, and also coefficient-wise total positivity for a Hankel matrix implies that the sequence is coefficient-wise log convex. So what that means is you take the polynomial an minus 1 times an plus 1 minus an squared. This polynomial has non-negative coefficients. So again, this was the theorem which I stated a while ago. Unfortunately, we do not have a theorem like this in this setting. We do not have necessary and sufficient conditions, but we have the following theorem. So this was discovered by Allen about 10 years ago, but then only published in this paper, which got published in 23, but it was out on the archive in 2018. So you start with a sequence of variables, alpha 1, alpha 2, etc. And define Sn of alpha to be a polynomial in these variables. So what you do is you take this continued fraction, 1 over 1 minus alpha 1t, 1 minus alpha 2t, and so on, and you expand it as a formal power series. You take Taylor expansion and collect the coefficients of t power n. So you have this parameter t, do Taylor expansion and collect the coefficient of t power n. Then the result is this sequence of polynomials is coefficient-wise Hankel totally positive. So every talk should have a proof. I will give you a sketch of proof for this. So the first fact you need to know about this. So by the way, these polynomials are called Stieltjes-Rogers polynomials. So the first fact you need to know about this is that these polynomials have a combinatorial interpretation. So first, let's consider a Dick path. So these are paths which start at the origin 0, 0. They end again on the x-axis, and you either go northeast 1, 1 or southeast 1, minus 1. And so the total number of Dick paths are Catalan numbers. Dick paths with length 2n. So now I assign weights to the steps. So whenever I have an up step going from height I minus 1 to height I, I give it a weight 1. And whenever I have a down step, I give it a weight alpha I. So these are the weights here. So this is alpha 1 because it's at height 1 to 0, alpha 2, alpha 3, and alpha. There are 2 steps from height 4, so both of them get alpha 4. And we say that the weight of the dict path is the product of all these weights. So for this, it's alpha 1, alpha 2, alpha 3 squared, alpha 4 squared. And this is the result of Flageolet. He showed, it's a very beautiful and very simple proof. It's a very beautiful result. He showed that these polynomials are simply, you take the sum over all dict paths of semi-length n and you add up all the weights. So I'll do an example. So for n equals 3, you have 5 dict paths. The Catalan number is 5. So here you have the weight of this is alpha 1 times alpha 2 times alpha 3. Then you have alpha 1 squared times alpha 2. And you proceed like this. And you add these up. And that is this polynomial S3 of alpha. This was what Flageolet proved. Now, I have given you an interpretation of the polynomials. I will show you very briefly how you can prove total positivity, that the Hankel matrix is totally positive. So for this, what you do is consider Z2 cross Z2, and this is your x-axis. This is the origin. This is 2, 4, minus 2, minus 4. So you take the even sublattice. Take all the points such that the sum of the coordinates is even. And this is an infinite graph. You construct this infinite graph. All the edges are, it's a directed infinite graph. The edges are directed to the right. So also the edges have weights. So all edges which are at this height get a weight alpha 1. All edges at this height, so all edges going up get weight 1. All edges going down, here they have alpha 1, alpha 2, alpha 3, alpha 4, and so on. Now notice that if you start from minus 2n and you go to 2k, such a path is a dict path of length 2 times n plus k. So the path matrix of this graph is the matrix whose entry at row n and column k is the weighted count of all paths starting at minus 2n, ending at 2k, and from the result of Flageolet, this matrix is exactly the Hankel matrix S0 alpha, and then S1, S1, S2, 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 and so on. And I will not tell you what the Lindstrom-Gesell-Vienno lemma is, but if you know what that is, it is the Lindstrom-Gesell-Vienno lemma says that the minors of this matrix count the number of non-intersecting paths on this graph. And since it is counting something, it should be non-negative. And this is how you prove this theorem. So Flageolet's lemma was known in 80, Lindstrom-Gesell-Vienno lemma was proved in the 1980s. But surprisingly, this was like both these pieces of information were only put together in in the last decade. The converse need not be true. This is what makes this story difficult. If you have a sequence of polynomials, which is coefficient-wise Hankel totally positive, it may not have a nice continued fraction.
Bishal,
Yes.
is there some corresponding result for Motzkin paths or Schroeder paths?
I'm going to get to that. Okay, so you've guessed my next slide. So here is an example. Let me give you quickly an example due to Euler. So again, Euler proved this continued fraction. So instead of n factorial here, if you replace that with x times x plus 1, so on x plus n minus 1. So these are rising factorials. So instead of doing 1 times 2 times 3 and so on, you do x times x plus 1 times x plus 2 and so on. Then you get this continued fraction. Since all of the coefficients here are non-negative polynomials, it implies that this sequence is coefficient-wise Hankel totally positive. So another example. So there are these things called Eulerian polynomials. Maybe I'll quickly brush over. So if you take Eulerian polynomials, these count descents in permutations. You have this continued fraction. This is a typo. It should be a y over here. So this shows that the Eulerian. So the upshot is, whenever you can write a continued fraction with non-negative polynomial coefficients, you get coefficient-wise Hankel total positivity automatically. How far can you take this? I'll get to that in a while. Let me tell you other classical continued fractions, as Manjul pointed out. So the S fraction or Stieltjes type continued fraction is one of a few other continued fractions which have been, when I say classical, considered in the large parts of the 20th, 19th and 20th centuries. And another type of continued fraction, by the way, in number theory literature and analysis literature, the terminology is slightly different. And I forget, but I think Stieltjes, one of them is called associated continued fractions, the other is called regular continued fractions. For the same objects, there are different names. So if you have a continued fraction that looks like this, so remember previously you did not have the gammas, you had alphas instead of the betas, but then you did not have a t squared, you had t's. So these are called Jacobi type continued fractions. And again, you have Thron type continued fractions which look very similar to Jacobi, except you do not have a square here. It's all t's over here. Now, similarly, Flageolet in his paper showed that the Jacobi type continued fractions are counted by Motzkin paths. So these are paths just like Dick paths where you have northeast, southeast, but you also have a level step. So you can also go across unit 1. And T fractions are counted by Schroeder paths. So you have northeast 1, 1, southeast 1 minus 1, and you have long level steps. So 2, 0, so 2 unit steps. And this was again, written down by various authors in the last decade. Let me first state this theorem about, yes?
So one quick question. So if you take the determinant of the Hankel matrix of Schroeder paths, then you get counting formula for tilings of estate diamond. Is there some connection with that?
So I'll get to it.
Okay.
So here is the statement about T fractions, which answers your question. So if you have a continued T fraction, so let's say alphas are variables, deltas are variables, and you define these polynomials from just like the previous theorem that I mentioned. Instead of an S fraction, you have a T fraction. Then the sequence is again coefficient-wise Hankel totally positive. And the proof is very similar. You have the Schroeder path interpretation, and you do Lindstrom-Gesell-Vienno, where you just add one more component to your graph. So you put level steps in between. So now you can also go from this to this, from this to this, and so on. So now I will answer, maybe I'll answer your question in more detail later. So if you have determinantal expression, of course, okay, I'll get back to your question later because I have several comments on Aztec diamonds. Let me quickly go to J fraction. Again, the converse need not be true. If you have a sequence of polynomials, it may not even have a T fraction, a nice T fraction. So these are now called the Thron-Rogers polynomials. This should have been a T. The story is different for J fractions. The existence of a J fraction does not guarantee Hankel total positivity, even for real numbers. But we have the following result. So if you have this continued fraction and you construct this tri-diagonal matrix, so it's all ones on the super diagonal, gammas on the diagonal, and betas on the subdiagonal. And if you ensure that this tridiagonal matrix is totally positive, that implies that the sequence of polynomials is coefficient-wise Hankel totally positive. Again, there are a bunch of typos as you can see on this slide. But so the story becomes quite different here and more involved. Just the existence of the continued fraction by itself is not sufficient to prove total positivity. And if some of you are familiar with theory of orthogonal polynomials, you know that tridiagonal matrices, it's the same tridiagonal matrix that appears in the theory of orthogonal polynomials. And there's a very close link. So I'm not going to go into that. The proof of this result uses the method of production matrices. So let me quickly end my presentation by telling what production matrices are. So let me just skip all of this. So you start with a matrix P, a doubly infinite matrix. You assume that it's either row finite or column finite. That is, at most finitely many entries in each row is non-zero, or finitely many entries in each column is non-zero. And you define the following matrix. So you define matrix A, where the entry in row n and column k is p power n. You take raise p to the power n, and you take the entry 0k. Now you might wonder, why come up with a definition that looks like this, but maybe you can think of it as walks on the natural line that start at the origin. It starts at 0, it ends at k, and it takes n steps, and whenever you take a step from I to j, whenever you jump from I to j, you're allowed to jump however you want in each step. You put a weight pij. That's the thing. And so the row finiteness or the column finiteness will imply that there are finitely many such walks of length n. So you'll have a finite sum. And again, now in this case, so you see there's a lot of lattice path combinatorics that's involved. So here you have another class of paths which are known as Lukasiewicz paths. I won't go into details, but here is the theorem. So the theorem is, if the production matrix P is coefficient-wise totally positive, then the matrix A is called the output matrix. The output matrix A is also, well, coefficient-wise totally positive. And this is the first part of the statement. And the column 0 of the output matrix, which is the sequence A n 0, is Hankel totally positive. So this gives you, so let me just recall. We started with, so one technique for proving coefficient-wise total positivity was existence of Stieltjes type continued fractions. But then I told you about how to go beyond Stieltjes type. And so far, one of the most powerful techniques in our arsenal is this production matrix method. But it's still far from, sufficient. It does not prove all the examples that we have, all the conjectures that we have. And whatever I have mentioned, other than Thron type continued fractions, all the previous ones are special cases. In fact, this tridiagonal matrix that I mentioned, so if P is, this production matrix is a tridiagonal matrix, this statement actually boils down to the result on J fractions that I mentioned 2 slides ago. So here is the strategy which we use when you're trying to prove these results. So the first step and the hardest step is to guess what the production matrix is. Because unlike Stieltjes type continued fractions, which you can compute using the Euler-Wiskowato algorithm, and you have a unique continued fraction, you can compute it, production matrices are highly non-unique. So you have to guess it. But once you have a guess, that usually is the hardest part of the process. Then probably in a few years you can prove that it is the production matrix. And if you can prove, and then you also hope that the production matrix is totally positive. And so, once you can guess the production matrix, you hope that you can prove it in a couple of years. But the hardest part is to get started. So here is a computational problem. I give you a sequence n, put the sequence in column 0 of an infinite matrix and fill the matrix such that the production matrix of this doubly infinite matrix is totally positive. How do you do that? And this is usually the hardest part which we try to answer. And it's usually like dependent on the problem we are trying to solve. So let me just finish quickly by some results and conjectures. So here is something I did during my PhD. So there are these class of permutations called D permutations. So these are all permutations on 2n, such that for every even index, 2i is bigger than or equal to sigma 2i, and 2i minus 1 is less or equal to sigma 2i minus 1. And now define this multivariate polynomial with infinitely many variables counting all of these different statistics on D permutations. I'm not going to tell you what these are counting, but you sum over all D permutations and you count many, many different things. Then you obtain this continued fraction. And so this implies that these polynomials are coefficient-wise totally positive with respect to all of these variables. Let me mention another conjecture. Some of you may have seen permutation patterns before. So let sigma and pi be two permutations, and we say that the permutation sigma contains pi if there is a subsequence of sigma that has the same relative order as pi. And avn of pi denotes the set of all permutations of length n which avoids that pattern. So what I mean is I do not want a subsequence inside my sigma that looks like pi. And this is a conjecture, it's a strong general belief of several people that for any permutation pi, you take the sequence of, you count these numbers, these sequences are Hankel totally positive by computation so far. Almost no proofs. Here is another example and a conjecture. So you take the number of labeled trees on n vertices, and by Cayley's theorem, this is counted by n power n minus 1. So let f and k be the number of forests with k labeled trees. So you take multiple trees, k trees, and you have n vertices. And you take these polynomials, you add up over all, you fix the number of vertices and you add up over all forests. This sequence is coefficient-wise Hankel totally positive. This was proved using production matrix method by Allen. And the sequence n power n, it counts the number of functions from 1 through n to 1 through n. And you can represent this geometrically by functional digraphs. So what you do is you take a graph where you have vertices 1 through n, and if f of I is equal to j, then you draw a directed edge going from I to j. These digraphs have the property that every vertex has out degree 1. So now consider let psi and k be the number of functional digraphs with k connected components.
Yeah, excuse me, Bishal.
Sorry?
So what about n to the power n minus 2, like number of Cayley's level Cayley's? So you have the rooted field. So if we define f and k to be n to the
Sorry,
power.
I can't hear you. Sorry, I can't hear you clearly.
So I'm saying, like, if you replace n raised to the power n minus 1 by n raised to n minus 2,
Yes.
there, because that counts the number of Cayley's tree.
Yes. So for rooted trees as well, that sequence is also Hankel totally positive.
Okay, that's interesting.
That is also Hankel totally positive, and you have refinements of that result as well. So you can introduce a statistic, introduce a polynomial, and which are coefficient-wise Hankel totally positive. So this was done by Chen and Sokal.
Okay, interesting.
Correct.
One more question, sorry, before we move
Yes.
forward. So like you have Catalan numbers and
Yes.
you have 1, 1, 1, all. So in this Hankel sequence, do you have any symmetry, like, or periodicity? Like, do you have any examples where they repeat the coefficient, or is it not
If they
possible?
repeat, if I am not wrong, I have to think about it, but I think if they repeat, they have to be a constant sequence. So one thing is the sequence has to be increasing sequence. It has to be monotonic, non-decreasing sequence. So if it's a Stieltjes moment sequence, it will be, so in fact log convexity will imply that it is non-decreasing.
Okay, so there's no periodicity of the phenomenon.
No.
Okay, fine. Thanks.
Yeah. So I have copied another slide from a talk that Alan Sokal gave at this seminar series which Gaurav Bhatnagar runs, Special Functions and Number Theory. So here again, he says that there are many cases where he finds empirically that a sequence of polynomial is coefficient-wise Hankel totally positive, but he is unable to prove it because there is neither a Stieltjes type continued fraction nor a Jacobi type continued fraction in the ring of polynomials, and maybe no. So I did not mention another technique which is branched continued fractions, which I did not go into in this talk. Or and then he puts a list of conjectures. So the first one has been solved in this list, which in an increasing sequence of difficulty, which he thinks like the one above should be more difficult than the ones below. So there are the Rook and Laguerre polynomials, there are Dom polynomials, Apéry polynomials, Boros-Moll polynomials, inversion enumerators for trees, reduced binomial discriminant polynomials. So this talk is there on YouTube, and maybe I'm advertising for it now. And then there's a long discussion after the talk where he talks about each of these sequences. The first of these have been proved. So it was independently by Baoshuan Zhu and it was only recently published. It was there on the archive a while ago. And also with Alex Diachenko, Matthias Petreol, and Alan Sokal, we have a further generalization of the Rook and Laguerre polynomials. Perhaps with this, I will end with some final remarks. I know I have gone slightly over time. So a lot of important combinatorial sequences seem to be moment sequences. Coefficient-wise Hankel total positivity generalizes the notion of Stieltjes moment sequences, and important combinatorial polynomials seem to be coefficient-wise Hankel totally positive. Existence of a nice Stieltjes type continued fraction implies that the sequence is coefficient-wise totally positive, but it may not exist. The production matrix method is a very powerful tool, but it's only a sufficient condition. It's far from necessary at the moment. And coefficient-wise Hankel total positivity, it's a big phenomenon. Many conjectures. We understand very little. Thank you.
Thank you, Bishal. Is there any question?
So might be an easy question, but do we want the product of two Hankel matrices or the sum of two Hankel matrices? I mean, is that again a Hankel positive matrix or?
Yes. So the interesting part is the following. So you can think about it just by moment sequences, right? So if you have integral x power n d mu is equal to an, and integral x power n d nu is equal to bn, then integral x power n d mu plus d nu is equal to an plus bn. So for the sum, it's pretty simple that it is a Stieltjes moment sequence. Unfortunately, it does not, like this addition, as you go to coefficient, as you upgrade from pointwise to coefficient-wise, it's no longer guaranteed that coefficient-wise this will be true. Same for products. So pointwise products, that is an times bn, I think that is still a Stieltjes moment sequence. You can take powers, you can take products, you can take sums, but none of these hold when you upgrade from pointwise to coefficient-wise. So if you're working with measures, if you're working in the real and analytic world, but as soon as you upgrade to algebraic world, I think things change. Or if it does hold, then it's a miracle, and you usually don't know how to prove it for like special cases.
So even in the pointwise case, we have a ring structure of thoughts on the set of all Hankel totally positive, right?
Sorry, can you repeat that?
In the pointwise case, we
Yeah.
see structure of sorts from the set of all Hankel totally positive, right?
You still have what?
Ring structure. Since you have addition. So,
No. I think it's not entirely a ring because you can't multiply. For example, you can't multiply non-negative reals to sequences. You cannot subtract.
yes.
So addition is allowed, but you cannot subtract.
So one other question was, if I look at the polynomials corresponding to, let's say, the binomial coefficients, right? Then do we have coefficient-wise Hankel positivity?
Yes. So let me show you. So let me take the central binomial coefficients. Okay, I mean, there are many conjectures, and some of them can be extremely difficult. Some of them are open. So if you take the central binomial coefficients, you see there's a 2 and then it's all 1s. These are the coefficients of the, so this is the sequence 2n choose n.
So now that we also know that polynomial corresponding to the binomial coefficients is totally Hankel positive and so on, we also know that these count the number of lattice paths. And there's a nice correspondence between lattice paths and partitions. So do these, I mean, are there any results?
Depends. I mean, you'll have to be more specific in the question. Sometimes that can help. Sometimes, not always.
And one last question.
Yeah.
So there was this result by Flageolet to sort of a characterization of coefficient-wise totally Hankel positive sequences. You mentioned that it has to be positive because it is counting something.
Oh, that's the Lindstrom-Gesell-Vienno lemma I was mentioning. LGV lemma.
So if I forget the fact that it's counting something, do I still have a proof that it's always going to be positive?
Oh, I don't think I understand your question. But I mean, okay, I don't think I understand your question. I mean, what do you mean by if you forget that it is counting something?
So is there a proof of the fact that it's positive independent of me taking into account that it's counting something?
Oh, well, the point is then you'll have to explicitly compute the determinants. Now the Lindstrom-Gesell-Vienno lemma tells you what the determinant means. So it simplifies your life by you having to avoid that computation. So in general, I mean, if you have, you have a determinant and you expand it out, you do Laplace expansion, you expand it out, the Lindstrom-Gesell-Vienno lemma, and you have a huge sum when you're trying to compute a determinant, right? The Lindstrom-Gesell-Vienno lemma gets rid of most of the terms in that sum. So, I mean, I would not know how to sort of avoid using that and still compute the determinant.
Thank you.
Yeah.
I just want to remind you that question regarding.
Yes.
Sorry, before you answer, can you please quickly answer one question by me? Because I have to be somewhere else.
Okay.
So, you know about Schroeder paths with barriers?
Schroeder paths with barriers. What do you mean by not really?
Just normal Schroeder paths, but then you put in some barriers where the path is not allowed to cross. So it has to jump over those barriers, right?
Okay.
That's studied in this
I mean, in the context of total positivity, so if your barrier is like if you're not allowed to go above a certain height, then that's not hard to study.
I see. Okay. So in this case, the barriers are vertical. Okay. So I mean, certain steps are not allowed basically. But I can give you the context. So this comes from the generalization of the aesthetic diamonds.
Okay.
And it turns out that counting the tiling picture is equivalent to counting these Schroeder paths with barriers. So these barriers are periodic in that sense, okay? Because of the way that the figure is. But anyway, so we can discuss this later also.
So if you say periodic, do you mean periodic and like? So there are two things, right? You can say that if you are, let's say, at modulo 3 let's say all the mod 3 steps cannot have so and so have these restrictions. There could be that, or you could say that at mod 3 heights, that is if your path reaches a certain height, then you put a restriction. So if you have restrictions which are height dependent and not, so which depend on the y-axis and not on the x-axis of the path, that's okay. You can handle with continued fractions. But if you have restrictions based on the x-axis as well, then you cannot handle that.
All right, thank you.
Yeah.
So there is another question by Ishika.
Yes.
So it is about what is your motivation and why
So-
you are considering this totally positive, why the minors are all positive here.
Oh, I see.
That is first point, and if I take negative, then this equivalent result.
Sorry, I can't hear you very well.
Okay, so what I'm saying is that if I consider the minor to be negative, then
Yes.
I consider the equivalence relation which we have. Is there any changes, or there are minor changes, or
Oh, right. So I mean, there are various things which people have studied. So people have studied something called, more generally, something called sign regularity. That is, minors of the same size should have the same size, same sign. But I myself have not studied that. And again, I mean, depending on what you're trying to study, the theory can be very different. So let me just tell you one fun fact. Total positivity is a language to state things. You can in fact state, I mean, if you make a statement regarding using total positivity, the theory can be very different depending on what sort of minors you're considering, what is the shape of your matrix. The theory can be entirely different. In fact, you can state the Riemann hypothesis. You can state the Riemann hypothesis as the total positivity of a matrix. So it's equivalent to conjecturing that a certain matrix is totally positive.
and what I am just
Yeah.
wondering that whether there is an obvious relationship between total positivity or total negativity. So that
So, again, I mean, if you have negative minors, you have a completely different theory. So people have studied that. At this moment, I will not be able to tell you more, but maybe I'm not sure if this is entirely true or not, but not for Hankel matrices, but for Toeplitz matrices, I think if you want that certain minors are negative, certain minors are positive, you have to put conditions on zeros of polynomials lying on certain sector of the complex plane, etc. So then you have certain analytic characterizations. So it's a completely different theory. I mean, you don't talk about measures there. You'll talk about something else there.